Welcome to this lecture. In the last lecture, we had looked at some very basic issues in software design, and then it said that it is important to distinguish a good design and from a bad design, and then we are trying to characterize what is a good design, and then we said that there are many factors that determine whether a design is good or bad, but correct implementation of the functionality, that is possibly the most important requirement of a good design, because unless it is a correct design, it is not a good design. But there are several design alternatives which we can come up with different alternate designs which are all correct, but then how do we decide which is a better design? And then we had said that understandability of the design is a major issue. We can rate a design solution to be good or bad based on its understandability. But there are two questions that arise now, that how do we know that which design is more understandable, because that is a debatable question, right, because somebody may say that this design is more understandable, another person will say that no, that is not a very understandable design. We should be able to tell more formally what we mean by a understandable design, and also we have to address this question that how do we really come up with a understandable design. So, let us proceed from that. First, let us look at the characteristics of a design that enhance its understandability. So, the first characteristic is the use of consistent and meaningful names, because unless the names in the design are meaningful in the problem context and also they have been used consistently, anybody trying to understand the design will get confused. All design components should have names that corresponds to the problem domain as far as possible, and they should be meaningful, somebody trying to understand. And the second characteristic of a design which is understandable is that it should have been decomposed well into modules. This we call it as the modularity of the design. We need to look at this question, that what do we mean by modularity, what is a well decomposed set of modules, that we will do next, but then this is an important characteristic, that the design should be modular and the modules should have been such that they have been well designed. Just arbitrary set of modules is not a good design, the modules should have been well decomposed, and also the call relationship should look like a tree diagram. This is also called as layering, because each layer of the tree is a implementation of the previous layer and a specification for the lower layer. This is a desirable characteristic, we will see why little later. That is, not only that we should have a well decomposed set of modules, but also their call relation should be representable in the form of a tree like diagram. Now, let us try to understand what we mean by modularity or a well decomposed set of modules. we say that a design is modular if the modules are almost independent of each other. A set of modules are almost independent of each other if they either do not call any other module or they call very less. If a module calls all other modules and it requires many parts to be completed by other modules and so on, then it becomes a dependent module. In a good decomposed, well decomposed set of modules, the modules should be as independent as possible. It is not possible to have a completely independent set of modules that no module interacts with other, but the interactions among the modules should be kept to a minimum. To understand why it is so, we will argue that this is actually the divide and conquer principle. A modular design uses the divide and conquer principle in the sense that to be able to understand the design, we just take up each module and then we understand, and if after we have understood all the modules, we have understood the design. But if the modules have complex relations, that is each module calls several other modules, then while understanding a single module, we need to also see what it gets done by the other modules and so on. So, as long as the modules do not interact too much, we can understand them well, because based on the divide and conquer principle. So, if the modules are independent, we can one by one we just look up the modules and understand this, and this is based on the design and divide and conquer principle. If a bunch of sticks are tied together and we try to break it, then it becomes very difficult, but if we take one stick at a time and break it, then it becomes very easy. It is just the similar thing here, is that the modules one by one we try to understand, we can easily understand, but trying to understand all modules interconnected, complex dependencies among modules, then if we start with one module, we see that we need to understand another module and the third module and so on. Another requirement is layering. A tree like call relationship among modules is a superior, whereas an arbitrary call relation is an inferior design. We will see why this is a good idea. The layering is a good idea. One is bug localization. If there is a bug, it does not affect the other modules here, only the ones that are below it. Whereas here, any bug can have effect on any other module. And when we see the bug symptom, that is a failure, we do not know what is the module that is having the bug. But here, if we observe a bug here, we know that either the bug is here or in the previous one, it cannot be here, we do not have to even look at this. A bad design can come up with a very complex set of module interactions, is not really a set of modules and interactions, it is is a diagram for some other purpose, but I am just showing it for illustration that it can look extremely odd, and for one module to understand it we might have to understand this module and then this module and then this module and so on. We will end up for understanding one we need to trace all modules and becomes very difficult to understand. We need a nice tree like diagram. So far we said that modularity is a set of independent modules, and said that independent modules are actually not practical, that all modules are independent. There will be some interactions between modules, but can we give a more meaningful characterization of modularity? We had intuitive understanding of what is modular, that modules are almost independent of each other, do not depend too much, represented in a tree like diagram and so on. Let us try to give a better characteristic or more precise characteristic of what is a modular design, and we will do that in terms of two concepts. One is called as cohesion and the other is called as coupling. A modular design should display high cohesion and low coupling, and if we understand these terms cohesion and coupling and we can measure them, then given a design solution we can check whether it has high cohesion and low coupling compared to another design which is given to us. So, let us try to understand how to measure, define cohesion and coupling. And of course, the modules should be layered. A good layering, a tree like diagram, we will see that it has low fan out abstraction. We will look at this concept as we proceed, but then let me just mention briefly that in a tree like diagram, if we want to, let us say, understand this module, then we see that it calls only the lower modules, and maybe we will have to look at these two. If we want to understand this one, then we do not even have to look at this. We know that this will call only its lower layer modules, and there are no, if there are no lower layer modules, then we can understand this, can understand this, and then based on that we can understand this and so on. But if it is a module structure like this, then we can't do that. To be able to understand one, we need to just go across all other modules and so on. It becomes very difficult. So, a tree like hierarchy, we have low fan out, that is, it depends on less number of modules, and also there is abstraction, abstraction in the sense that these are, we can consider these modules are implementation of this module, and therefore, you start from the leaf layer modules and then look at more concrete module and so on. This is an illustration of how bad it can become if the modules are having lot of dependencies. So, this there are no dependencies. This there are very less number of dependency, but look at here that there are very high dependencies across modules, and it becomes very difficult to understand, maintain this kind of design. We would rather go for this, if not go for this. Now, let us see the concepts of cohesion and coupling. If we can determine the cohesion and coupling of a given design solution, we can tell that whether that is a good design or bad design. We say that a module is cohesive if it performs a single task or function. If it tries to do too many things, then it is not cohesive. On the other hand, the coupling is defined between two modules. Two modules are coupled if they dependent on each other. So, that they exchange some data items, call each other, and then we say that these are coupled modules. So, this is two important concepts. Cohesion is, we define it for a single module, and then we say that a single module is cohesive if it performs a single task. If it does many things, then that is not really cohesive. And coupling is that how much dependent one module is on another module. If they exchange too many data items, call each other frequently, exchanging data items and so on, then they are highly coupled. But if they do not call each other, there is no data exchange between two modules. We say that these two modules are independent, and if that is the characteristic of almost every module, we will say that there is independence, and similarly they are cohesive, there is a high cohesion and low coupling, then we say that this is a good design. Now, let us look at how do we determine the cohesion and coupling. Before that, if a design solution we find that it has high cohesion and low coupling, then we say that is a functionally independent set of modules. So, there each module is doing some function independently, it is not dependent on others, and the term that we use is functionally independent. So, the goal of any good design technique is to come up with a functionally independent set of modules. But we should be clear why we want a functionally independent set of modules. As we said that this results in better understandability, this functionally independent set of modules compared to a highly dependent set of modules. If we have a functionally independent set of modules, the complexity in the design is reduced, and we can take up one module at a time, quickly able to understand. Similarly, we can, if there is a bug, we know that which module it contains the bug, otherwise we might see that whether it has come from some module to which it has called. So, if there is a bug while executing this design module, we observe it, then it might have come from here, or it can have come from here, etc. So, an error debugging becomes easy, and also understandability is easy, and not only that, we can reuse module. Let us say this is a module and we want to use it in another project, we can just take this and use it there. But here observe it that if we want to use this module in another project, we will see that this needs help from here and this in turn needs help from here, and similarly this needs help from here and so on. So, they are all coupled. We cannot just take one module and use it, we have to take across all these modules, the entire project we have to take, and that becomes infeasible. So, if we have a functionally independent set of modules, any module that we need in another project, we can easily reuse that. Each module in a functionally independent set of module has well defined precise functions, and it does not interact with other modules, and or if at all it interfaces with other modules, it is simple and minimal, and therefore, becomes easy to reuse modules. But how do we measure functional independence? Even though we know that a functional independent set of module has high cohesion and low coupling, can we look at a design and say that whether there is a high cohesion and low coupling? Let us try to explore this further. We will classify the different types of cohesion and coupling, so that given a design we will try to see which class of cohesion and coupling it has, and based on that we will say that whether it is cohesive, highly cohesive and low coupling, etc. First, let us look at the cohesiveness, and let us try to classify what are the type of cohesion, so that if we look at a design, we will see that what sort of cohesion it has. Let us see the different types of cohesion. We can look at a design and we can say that it has any one of these 7 types of cohesion. You can look at a module and you can say that this module has either this coincidental, logical, temporal, procedural, communicational, sequential or functional cohesion. If it has functional cohesion, then it has high cohesion, it is a good design, but if it has coincidental cohesion, on the other hand, it is not a good design, and something in between is moderate cohesion. And we want to look at all modules and see what type of cohesion are there. If most of them have high cohesion or a slightly moderate cohesion, we will say that the design is good or okay, but if they have low cohesion, we will see that we will say conclude that it is not a good design. First, let us look at the worst form of cohesion, it is called as the coincidental cohesion. Here, if we look at the module, look through what functionality it has, we will see that the functions are rather random collection of the functions. There is no thinking or plan behind putting some functions in the module, just taken out random functions and made them into a module. Just to give an example, let us say we look at one module, some name AAA, and then it contains the functions print inventory, register student, issue book. So, these actually correspond to the functionalities required by various various requirements. Print inventory is part of some inventory functionality, register student is some registration, issue book. So, these are random set of functions, they do not neither belong to the same requirement nor there are any relationship between these functions. And if we ask that what does the module A achieve, we cannot really answer. Say that okay, it does some part of the inventory, does some registering student, it also does issue book, etc. So, there is no single thing, single function that this module achieves. It does various things here and there. Somebody has just put these modules randomly into this module AAA, and this we call as coincidental cohesion. We consider logical cohesion, module has logical cohesion if all elements, all functions in the module perform similar operation. For example, all functions in a module are doing error handling, or all functions in a module are reading the data input, or all functions in a module are just printf kind of thing, data output. Then we say that this module has logical cohesion. That is, the functions are logically related, that they are doing similar things, and that is why the designer has put them there. And this is also not a very good form of cohesion, slightly better than coincidental cohesion, but still it is not good. Let us look at an example of logical cohesion. Let us say we look at a module and find that its name is print, and then it does various types of printing across various functionalities, printing grade, certificate, salary, etc. These are part of various other functionalities or requirements. And then we say that this module has logical cohesion. It is not the bottommost cohesion, but still it is not a good cohesion. Next, we will look at the temporal cohesion. We will stop here, continue in the next lecture.